Throughout history, man has invented many devices for telling the time. Nowadays, we use a modern digital watch, which can tell time to within hundredths of a second routinely. Previous generations, however, have made use of more primitive technologies, such as this hourglass. Despite the fact that the technologies involved in these two devices are worlds apart, they have something rather surprising in common. They both rely on silicates for their operation. In the hourglass, the silicate is the sand. In the digital watch, the silicate is the quartz crystal, whose frequencies of vibration maintain its accuracy. Silicates form a large part of the Earth's surface. In fact, they constitute about 93% of the Earth's crust. That's why so many of our artifacts and materials contain silicates. For example, many precious and semi-precious stones consist largely of silicates, as does the clay in this clay pipe, and the talc in this talcum powder. And again, this old-fashioned radio condenser has mica in it, which is another silicate. What then are silicates? Well, to answer this question fully would involve us in a tremendous amount of physics, chemistry and geology, and we don't want to do that. What we'll do is we'll look at a particular aspect of silicates. In fact, we'll look at silicate structure and how they are classified into a particular scheme. The classification scheme is based on geometrical principles of structure and organization of the constituent atoms in the silicates. So, what atoms are present in silicates and how are they arranged?
Well, first of all, then, as to the atoms themselves. Now, any silicate must contain the two elements silicon and oxygen. There will be various other substances present, magnesium, aluminium, and so on, but nevertheless, it's the silicon and oxygen atoms and the way in which they're combined together that really determines the structure of a silicate, and that's our concern today. Now, to demonstrate these structures, we're going to use what are called ball and stick models, and I've got one here. It's a very simple model, just consists of a number of balls, different colors representing atoms, and the rods or sticks represent the joins between them. It's sufficient for our purposes because it shows us the relative positions of the atoms, and it also shows the way they're joined together. These black balls here represent silicon atoms, and the red balls represent oxygen. And as I've said, you have the chemical bonds, the sticks, between the two. Now, silicon and oxygen have a very strong affinity for each other, and they combine together into groups of various sizes. If you look at this model, we can see that this silicon atom is joined to 1, 2, 3, 4 oxygen atoms, and this oxygen atom here is joined to just 2 silicon atoms. Now, that in fact is the preferred arrangement. We say that silicon has got 4 bonds and oxygen has got only 2. If we take a group like this one I've got here, now the silicon is still joined to 4 oxygens, so all its bonds are used up. But what about the oxygen? Each oxygen atom has only got 1 bond joining it to the central silicon atom, so it's got 1 bond still free. And any group of atoms like this, which has got 3 bonds, is what we call an ion. This particular one is the silicate ion, and here's its chemical formula. The Si denotes the silicon atom, the O4 refers to the 4 oxygen atoms, and the -4 to the 4 free bonds. Don't worry too much about the minus sign. Now, any silicate is going to contain lots of these silicate ions. The free bonds will attach themselves either to other silicon atoms or to other metal ions, and the end product is going to be a structure something like the one I've got here. This one, I believe, is one of the pyroxene group of silicates. You can see the silicate ions. There's one down here, look, marked off in yellow, and there's another one up here, and there are various metal ions scattered around. It's all very complicated. And the question we're going to have to face today is how can you make sense of any structure as complicated as this one?
Well, we discussed the complexity of geometric structure in the unit, and there, you remember, we showed you 2 aspects. First of all, there were the basic geometric elements, And secondly, there was the fundamental geometric arrangements. Now we've only got one geometric element essentially that we're looking at, and that's the SiO4 ion. If you look at it closely, you'll see that the oxygen atoms arrange themselves at the corners of a tetrahedron. Now why is this? Well, let's take a look at a more realistic model. Here we've attempted to show the spheres of influence of the various atoms. The clear spheres show the oxygen atoms, and the small black sphere in the center is the silicon atom. You will notice that the most compact way in which the oxygen atoms can arrange themselves around this small silicon atom is in this tetrahedral arrangement shown. So, our basic building block is a regular tetrahedron, a simplex in fact. Okay, we're modeling silicate structure with these tetrahedra. So let's see how far the model can take us by looking at the arrangements of tetrahedra that can occur. First of all, let's look at the simple arrangements where we would consider moving the tetrahedra parallel to themselves in unit distances along 3 different directions. If we arranged our tetrahedra in this way, we would end up with the 14 possible 3-dimensional Bravais lattices, which you have already met in the text. The first type is the cubic lattice, of which there are 3 varieties. Then there are 2 tetragonal types, 1 trigonal, 4 orthorhombic, 2 monoclinic, 1 triclinic, and finally a hexagonal lattice type. Over here we've got 2 models of the extreme cases. The first model shows the most symmetrical lattice of all, which is the cubic lattice. Notice here that the 3 directions are all at right angles to each other, so they're angles at 90 degrees, and also that the unit distances between adjacent ions in the lattice are all equal. This particular lattice occurs naturally as the crystal structure of common salt, sodium chloride, and in that particular crystal the sodium and chlorine ions alternate throughout the lattice, whichever direction we go in. The other extreme case of Bravais lattices is the triclinic lattice, which has the least amount of symmetry. Now, the 3 unit distances are all different, as also are the 3 angles between the directions. If we arranged our tetrahedra on a lattice of this type, the tetrahedra would be all parallel. We would only take account of their position, their relative positions, and not their orientations or how they might be combined together, nor would we take account of what other atoms or ions were present. But in real silicates, the situation is much more complicated than this. The tetrahedra don't just arrange themselves in parallel arrangements of this type. They group themselves together in larger or smaller arrangements. And also, they are orientated differently. Furthermore, there are many other ions and atoms present in any real silicate, in addition to the silicate itself. So, to see what's really going on, we must now take a closer look at the free bonds, which we've been ignoring up to now.
Well, if you remember, oxygen has got 2 bonds, so it prefers to join itself to 2 silicon atoms. And one way of doing this is demonstrated in this model I've got here. We've got 2 tetrahedral groups which are actually sharing 1 central oxygen atom. So it certainly is joined to 2 silicon atoms and is quite happy. The way in which the oxygen atom contributes to the geometry of the tetrahedra is best illustrated by this sphere packing model over here. Look at the sphere of influence of the shared oxygen atom. It plays its part in this tetrahedron at this end, and equally well this tetrahedron at this end. But what's happened to the ratio of silicon to oxygen? Now, for a single tetrahedron, of course, we've got 1 silicon to 4 oxygens. Let's count what we've got here. We've got 2 silicons. We might expect 8 oxygens, but we don't have that many. We've got 3 at this end, and we've got 3 at this end, and 1 in the middle, 7 altogether. So the ratio has gone down from 1 to 4 to 2 to 7, or in other words, 1 to 3.5. What about the free bonds? Well, those are the unshared oxygen atoms Here we've got 3 at this end and 3 at this end, so instead of 8 we find only 6. And the chemical formula for this group then is Si2, the 2 silicons, O7 for the 7 oxygens, and -6 for the 6 free bonds. Well, that then is the way in which we group 2 tetrahedra together. But you remember, any one tetrahedron has got 4 corners, so we could in this way link it to up to 4 others. Let's just see what we can do by constructing things like this. Now I'm going to use a different model, one over here, where you see I now show the actual tetrahedra, and I show the fact that they're sharing a common oxygen atom simply by showing them joined together at a corner. And let's see what we can do like this. Supposing I were to take one more tetrahedron and link it onto the end of this thing, something like this. Now I think you'll see better what's happening if you look at it from a different angle. And if you look down from above, you get this picture. Well, this group has got 3 silicons, 1 for each of the tetrahedra. So you might expect it to have 12 oxygens, but in fact, of course, it's only got 10 because 2 are shared here and here. What about the free bonds? Well, the same thing. We have the unshared corners here, 3 at this end, 3 at the other end, and 2 in the middle, so 8 altogether. And the formula for this group is Si3, O10, and -8. Well, I can carry on like this. I can take a 4th tetrahedron, and I can tag it on to the end of this group. You can see what's happening. It's already beginning to look rather like a chain. The formula for this is going to be Si4, O13, because now we've got 3 oxygens shared, and 10 free bonds. I could go on like this. I could take a 5th tetrahedron and I could put it on to the end. And in this way, I'm just building up a lengthy chain. I could go further and add on more and more and build up chains of any length I like. Well, that's a one-dimensional structure, but that's not the end of the story. Let's go back to the case of just the 4 tetrahedra. I put one on the end, but I didn't have to do that, you see, because look, there's a free corner around here, and I could put one on there. So now I have 1 central tetrahedron surrounded by 3 others. The formula is exactly the same as before, because you see we still have precisely 3 shared corners. If I now come to put on a 5th or a subsequent tetrahedra, I can stick them onto the end, but the important difference is I now am building up a 2-dimensional structure. Nor is that the end of the story. You see, this 5th one doesn't have to go there, because there is, if you look, a corner free up here on the central tetrahedron. Well, that's going to be a bit tricky, and I've got a model already prepared for that. If I get rid of this, here you can see it quite nicely. It's beautifully symmetric. 1 tetrahedron in the center and 4 surrounding it. The important thing now is that I've got a 3-dimensional structure. Anything I build up from this is going to be 3-dimensional. So I can build up 1 dimension, 2 dimensions, 3 dimensions. Apparently I can go on indefinitely. Does this mean then that there are in fact infinitely many possible silicate structures?
We can answer Roy's question with a definite yes. There are theoretically an infinite number of possibilities. So, to make sense of them all, we need some sort of classification scheme. Now notice that all of the structures Roy has looked at so far have consisted of a relatively small number of isolated tetrahedra joined together in vertex-to-vertex contact. We're going to lump these together and call them type 1 silicates. So we have that the first class is type 1 silicates consisting of isolated tetrahedral groups connected in a tree-like arrangement. A special case of an isolated group of tetrahedra exists where we only have single isolated tetrahedra. Here's an example of a substance of that type. It's called zircon. The tetrahedra are separated by zirconium atoms, which we show as orange in this diagram. There are lots more examples of the same type, or in which we have 2 or 3 tetrahedra joined together in this way, such as, for example, melilite. Now, one type of structure which Roy has not looked at is a structure in which we have a ring arrangement. In graph terminology, the tetrahedra organize themselves in the form of a cycle rather than a tree. Here we have an example where there are 6 tetrahedra arranged in a ring of this type. Notice that there are 6 silicon atoms, 1 for each tetrahedron, and 18 oxygen atoms, 6 of which are shared, leaving 12 free bonds. So the formula is Si6O18 to minus 12. A real example of a silicate of this type is the mineral beryl. Again, we have in this mineral isolated rings of tetrahedra separated by various other ions, such as beryllium, which take up the free bonds. There are lots of other examples also with larger or smaller rings, or with multiple rings. Let's group them again all together into the type 2 silicates. So we have type 2 silicates have isolated rings of tetrahedra. Now the 2 types of silicate we've seen so far consist essentially of finite groups, small, relatively small finite groups of tetrahedra. The next most general thing we could do would be to look at long, essentially infinite chains of such tetrahedra forming a one-dimensional arrangement like this. They're rather like polymer chains. The group of minerals known as pyroxenes consists largely of this type of silicate, and jade is a good example of pyroxene. What happens is that the long chains line up in isolated strands forming a parallel regular arrangement. Now, in addition to single strands like this, we often find that double strands occur, like this. In this case, we get what looks like a ladder arrangement, and the holes in between the rungs are filled by various other ions, which take up the free bonds. A mineral of this type is hornblende. It's not difficult to see that it's possible to form triple strands by bringing another strand alongside of the double one. And multiple strands of higher orders can be formed in the same sort of way. We're going to classify all these types together as our type 3 silicates. We have, therefore, type 3 silicates consist of multiple chains of tetrahedra in which the length of the chains is very much greater than the width.
Well, the next generalization is pretty obvious. We've now got to start considering arrangements of tetrahedra in 2 dimensions. And this model I've got here demonstrates. If you look at the top layer, I've got a 2-dimensional sheet of tetrahedra joined together. Actually, if you look at it, this particular one is made up of a number of rings of tetrahedra which are meshed one to the other. Also, you can notice that I not only have the top layer, I've actually got a double layer, because there's another layer down here, and it's quite tightly bonded to the first layer by various metal ions. These bonds are strong, and they're very much stronger than these other bonds down here connecting to the next multiple layer. These are fairly weak bonds, so weak that one group of layers can slide relative to the other. The consequence of this is if we take actual examples of this kind of silicate, and I've got one here, this is soapstone. If you grind this stuff up, you in fact get talcum powder. If I feel it, it actually feels soapy, because even the pressure of my finger is enough to separate the layers out. The effect can be even more dramatic than that, because over here I've got mica. Do you remember the old-fashioned radio condenser we saw at the beginning of the program? Well, this is the insulator which is inside it. And in this case, you can see the stuff is actually quite flaky. You can see the layers are really quite ready to break up one from the other. Well, this then gives us our next classification. These are what we call type 4 silicates, in which we've got multiple layers of tetrahedra, the layers being separated by other ions. And finally, we come to the most intricate type of arrangement of tetrahedra. This is where we have each tetrahedron linked to 4 others, rather as we did in this model we saw earlier. Now, of course, the arrangements of the tetrahedra can vary, and you can get all sorts of 3-dimensional structures from it. I've got one over here, actually. And if you look at this, you can see that this, in fact, is an example of the structure we were talking about. If you take any one of the tetrahedra, like for example this one here, it is linked to 4 others. Now a three-dimensional structure like this is the kind of thing you find in quartz, and it's the intricate connections in all 3 dimensions which are the reason why quartz is so hard. And this then is our final classification. These are the type 5 silicates, where we have an arrangement in 3 dimensions, and the most important thing is that the connections are very strong in every direction.
So we've now constructed 5 types of silicate. The first consists of isolated tetrahedral groups arranged in a tree structure. The second type is where they are arranged in rings. And the third type has been these long one-dimensional strands forming polymer-like arrangements. Then the fourth type of silicate is where the tetrahedra have arranged themselves into 2-dimensional layers. And then finally, the 5th type is where we have the most complicated 3-dimensional frameworks arrangement. So our classification scheme has been based on the interconnection between tetrahedral groups. To a geologist, of course, this is not sufficient information. He would have to look in more detail at the geometry and how the tetrahedra are angled relative to each other. He would also need to know some chemistry, which ions are present, and so on. But nevertheless, despite these drawbacks, our classification scheme has given us a good, useful framework for investigating the characteristics of these naturally occurring silicate structures.